The production of railway wheels has seen significant advancements with the introduction of new technology that seamlessly integrates all manufacturing steps into a single efficient machine. This innovative approach eliminates the need for intermediate warehousing, streamlining the entire process and enhancing productivity. Central to this advanced production line is a rotating furnace, an impressive structure with a diameter of 23 meters. This furnace is capable of handling a production capacity of 40 tons per hour, underscoring its efficiency and the substantial volume it can process. The furnace's design ensures uniform heating, which is critical for maintaining the quality and integrity of the railway wheels being produced. Following the heating process, the production line features two powerful hydraulic presses. These presses are essential for shaping the heated metal into the desired wheel form. The first press boasts an extraordinary capacity of 9,000 tons, while the second press, with a capacity of 5,000 tons, provides additional shaping and precision. This combination of presses ensures that the metal is formed accurately and consistently, meeting the stringent standards required for railway wheels. The integration of these presses within the same machine eliminates the delays and inefficiencies typically associated with moving materials between separate stages of production. One of the standout features of this new production line is its impressive production rate. The system is capable of producing up to one railway wheel every 58 seconds. This rapid production rate is achieved without compromising on quality, thanks to the precision and reliability of the integrated machinery. The ability to produce a wheel in such a short time frame significantly boosts overall productivity and meets the high demand for railway wheels. Another critical component of this advanced production line is the rolling machine, which is equipped with 13 computer-controlled axes. This high-tech rolling machine allows for precise control over the shaping and finishing of the wheels. The computer-controlled axes ensure that every wheel is produced to exact specifications, maintaining consistency and quality across the entire production run. The machine's versatility enables it to handle a wide range of wheel dimensions, with the capability to produce wheels up to a diameter of 145. The integration of these advanced technologies within a single production line represents a significant leap forward in the manufacturing of railway wheels. By consolidating the heating, pressing, and rolling processes into one seamless operation, the need for intermediate warehousing is completely eliminated. This not only reduces the space required for production, but also minimizes the handling of materials, thereby reducing the risk of damage and improving overall efficiency. The forging of railway wheels is a critical process in the railway industry, ensuring the safety, durability, and performance of trains. Lucchini RS, a renowned company in the sector, has perfected the traditional technology of forging railway wheels, combining decades of expertise with meticulous engineering to produce wheels that meet stringent standards. This extensive overview delves into the various stages of forging railway wheels, elucidating the intricate details and precision involved in each step. Historical context and evolution of wheel forging. Railway wheel forging has a rich history, evolving significantly since the early days of rail transport. Initially, wheels were cast from iron, but the demands of increased loads and higher speeds necessitated stronger and more reliable manufacturing methods. Forging emerged as the superior technique due to its ability to produce wheels with excellent mechanical properties, such as enhanced strength and resistance to wear and fatigue. Lucchini RS, with its long-standing heritage in metallurgical processes, has been at the forefront of this evolution, continually refining traditional forging methods to improve wheel performance and longevity. Raw material selection and preparation. The forging process begins with the careful selection of raw materials. High-quality steel is chosen for its robustness and suitability for enduring the harsh operating conditions of railway environments. The steel is typically sourced in the form of billets, which are cylindrical bars of steel. These billets undergo rigorous quality checks to ensure they meet the specific chemical composition and mechanical properties required for railway wheels. Once the billets pass the quality inspection, they are cut into appropriate lengths based on the size of the wheels to be forged. This step is crucial as it determines the amount of material available for the subsequent forging operations. The billets are then preheated to a precise temperature range, typically between 1,200 degrees Celsius and 1,300 degrees Celsius, to make them malleable for forging. This preheating process must be carefully controlled to prevent overheating, which can lead to material defects, or underheating, which makes the steel too hard to forge efficiently. Forging process. The core of the traditional forging process involves several key stages: upsetting, preforming, and final forging. Each stage is meticulously executed to shape the billet into a rough wheel form and refine it into the final product. Upsetting. In the upsetting stage, the preheated billet is compressed longitudinally to increase its diameter and decrease its length. This operation is typically performed using a hydraulic press or a mechanical hammer. The goal is to create a blank with a cross-sectional area that approximates the dimensions of the final wheel. Proper upsetting is crucial for ensuring uniform material distribution, which is essential for achieving the desired mechanical properties and structural integrity. Preforming. Following the upsetting, the billet undergoes preforming to begin shaping it into a wheel-like form. This involves a series of forging operations using specially designed dies and punches. The billet is repeatedly pressed and shaped to create a rough outline of the wheel, including the hub, web, and rim. Preforming is a critical step as it sets the stage for the final forging, ensuring that the material flow is properly directed to achieve the correct geometry and structural characteristics. Final forging. The final forging stage involves precision forging to achieve the exact dimensions and final shape of the railway wheel. This step is carried out using a combination of forging presses and dies specifically designed for the wheel's profile. The wheel undergoes multiple forging cycles, each refining its shape and enhancing its mechanical properties. Throughout this stage, careful attention is paid to maintaining the temperature of the steel, as temperature fluctuations can lead to defects such as cracks or uneven hardness. Heat treatment. After the final forging, the wheel undergoes a series of heat treatment processes to enhance its mechanical properties and ensure uniformity. The primary heat treatment operations include quenching and tempering. Quenching. Quenching involves rapidly cooling the forged wheel in a quenching medium, such as water or oil. This rapid cooling process increases the hardness and strength of the wheel by transforming the microstructure of the steel. Quenching must be meticulously controlled to avoid introducing stresses or distortions in the wheel, which could compromise its performance and safety. Tempering. Following quenching, the wheel is tempered to reduce brittleness and improve toughness. Tempering involves reheating the wheel to a lower temperature and then allowing it to cool slowly. This process relieves internal stresses and refines the microstructure, resulting in a balanced combination of hardness and toughness. The precise tempering temperature and duration are carefully determined based on the specific steel grade and desired mechanical properties. Machining and finishing. With the heat treatment complete, The wheel undergoes machining and finishing operations to achieve the final dimensions and surface quality. CNC, computer numerical control machines, are typically used for this purpose, ensuring high precision and consistency. The machining process involves turning, drilling, and milling to create the wheel's final geometry, including the hub bore, mounting holes, and tread profile. Surface finishing is the final step, which may involve grinding and polishing to achieve a smooth and defect-free surface. This is crucial for ensuring optimal contact with the rails and minimizing wear. The finished wheel is then subjected to a series of rigorous inspections and quality checks to ensure it meets all dimensional, mechanical and surface finish requirements. Quality control and testing. Quality control is an integral part of the wheel forging process at Lucchini RS. Each wheel undergoes a comprehensive series of inspections and tests to verify its conformity to stringent standards. Key quality control measures include dimensional inspection, using precision measuring tools and equipment to verify that the wheel dimensions are within specified tolerances. Non-destructive testing, NDT. Techniques such as ultrasonic testing, magnetic particle inspection, and dye penetrant testing are employed to detect any internal or surface defects. Hardness testing, measuring the hardness of the wheel to ensure it meets the required specifications. Microstructural analysis, examining the microstructure of the steel to verify that the heat treatment processes have achieved the desired microstructural characteristics. Mechanical testing, conducting tests such as tensile strength, impact resistance, and fatigue testing to assess the mechanical properties of the wheel. Each wheel that passes these rigorous quality control checks is marked with a unique identifier and certification, ensuring traceability and accountability.